What are the practical implications there?
Oh, the practical side is huge. Think about the standard way. Collect sample, go to lab, run tests. That takes time. Hours, maybe.
Yeah, easily.
The best model in this work, using data already available from the system, could spit out a forecast for ammonia or DO in about 15 minutes.
15 minutes. Okay, that's basically real time.
It's near real time, yeah.
Okay.
It shifts you from reactive monitoring, finding out hours later you had a problem, to proactive management.
You get a heads up before the ammonia spike gets critical or before the oxygen dips too low.
Exactly. You see it coming.
Yeah.
A whole new era of communication in the global aquaculture industry is coming. Now you have the brightest minds in aquaculture right in your pocket. And what's best? You can listen to all of them while driving to a farm, traveling, or running errands. It's never been this good, and it's never been this simple. Welcome to the Aquaculture Podcast Show, the first AI-based podcast in aquaculture, where you'll find cutting-edge insights in everything that's working in aquaculture, nutrition, health, and production.
Welcome to the deep dive. Today we're jumping straight into something absolutely core for aquaculture success. We're talking about water quality, especially in those outdoor recirculating systems. Think red tilapia farms, keeping that water environment pristine, stable. Well, it's not just nice to have, is it?
No, not at all. It's completely fundamental. Your fish health, their survival, hitting growth targets, it all hinges on that water.
Absolutely.
And anyone managing these intensive systems knows it's a constant challenge. Things change.
The environment isn't static, temperature, sunlight.
Exactly. And the system itself is always, shifting dynamically. Plus, the standard way of checking, grabbing samples, lab work.
It's accurate but slow.
It is accurate, but yeah, there's that delay. You're often looking at results from hours ago, so you're reacting to the past, really.
Not managing the present, let alone the future. That delay can be critical. So that's our mission for this deep dive. Exploring some pretty interesting recent work on this, looking at how more advanced ways of analyzing data might actually predict key water quality parameters.
Giving you a peek into the near future of your system.
Yeah, this is based on findings from work focused specifically on red tilapia in an outdoor recirculating setup, how they use data to build forecasting models.
Right. So we're going to unpack that. What parameters were they actually looking at? And importantly, what factors turned out to be the key drivers, the things you really need to watch to make predictions.
And how well did the different prediction approaches work? Did one stand out?
Exactly. And then the big question, what does this mean practically? How can this kind of predictive power actually help operators manage things better, get an edge?
Okay. And the specific parameters they focused on are the big ones, the ones you're always tracking. Dissolved oxygen. Critical pH balance, those key nitrogen compounds, total ammonia and nitrite.
Always a concern.
And alkalinity, too, the system's buffer.
Yeah, the essential vital signs for the system's health, basically.
So this work involved data from a real production-scale outdoor system, right? Not just a lab experiment.
That's right. A functioning system raising red tilapia, set up with different zones for treatment, nursing, grow out. They collected data over about 3 months, and it was running under, pretty standard operating procedures, normal stocking densities, automated feeding, continuous aeration, the usual setup.
Good. So relevant data, and collecting that data consistently is always step one for this kind of work.
Definitely. They gathered daily measurements for a whole range of things: dissolved oxygen, temperature, pH, the nitrogen compounds, alkalinity, even water transparency.
So building up that detailed picture of how the system behaves day to day.
Exactly. A historical record.
Yeah.
Then the approach to building the models was quite methodical. First, you got all this data, right? But not everything you measure is actually going to be super useful for predicting one specific thing, like, say, ammonia.
Right. Too much noise, potentially.
So they first used an analysis method to basically filter through all those variables, to pinpoint the top few factors that really had the most influence, the most predictive power for each target parameter.
Finding the key ingredients, you could say.
Yeah, that's a good way to put it. Finding what really drives the outcome.
Smart. Avoids complicating the models with stuff that doesn't really matter. So once they had these key influential factors identified, what next?
Then they took those key factors, the high impact ones, and used those as the inputs to actually build the predictive models. They tried out a few different advanced modeling strategies. One was a kind of combined approach.
A hybrid.
Yeah, basically combining strengths from different types of analytical techniques, seeing if blending, say, statistical methods with some machine learning ideas gives you a better result.
Okay, so find the drivers, build different models based on them. The crucial question then, did it work? How well could they actually forecast those water quality parameters?
And this is where it gets quite encouraging, I think. For most of the parameters, dissolved oxygen, total ammonia, nitrite, and alkalinity, the results were actually very promising.
Oh, really?
Yeah. That combined or hybrid analytical approach generally came out on top. When they fed it enough historical data, the values it predicted lined up really well with the actual measured values later on.
That's potentially a big deal for managing those key parameters. Reliable forecasts for DO, ammonia, nitrite, alkalinity. That's huge.
It is.
Let's dig into the why a bit. Which factors were most influential for each one? What they find was driving dissolved oxygen, for instance.
Okay, for DO prediction, the analysis pointed to temperature, nitrite levels, and alkalinity as the top three.
Which makes intuitive sense, mostly.
It does align well. Temperature, obviously warmer water, holds less oxygen. Basic physics.
Hey.
Nitrite. Well, the whole nitrogen cycle involves bacteria that consume oxygen, so nitrite levels reflect that activity.
Oh.
And alkalinity. Maybe less direct for DO at first thought, but it buffers pH, and pH affects biological activity rates, which in turn impact oxygen consumption and production.
Ah, okay. It's all interconnected. Got it. What about total ammonia? That's often the first big worry in the nitrogen cycle.
For predicting total ammonia, the key factors were water transparency, alkalinity, and dissolved oxygen.
Transparency. Interesting. How does that play in?
Light penetration affects algae. Photosynthesis during the day uses CO2, raises pH, making any ammonia present more toxic. At night, respiration produces CO2, lowering pH.
Okay.
And alkalinity is the buffer against those pH swings. So it influences that toxic ammonia versus non-toxic ammonia balance. And DO, of course, is needed for the bacteria that convert ammonia downstream.
It really is like a complex dance, isn't it? Everything affects everything else.
It is.
So what about nitrite, the next step in that chain? What predicted that best?
For nitrite, the most influential factors were alkalinity, temperature, and total ammonia.
That seems very direct.
It reflects that nitrification process pretty clearly. Nitrite comes from ammonia, carried out by bacteria. Temperature drives the speed of those bacteria. Alkalinity provides the stable, buffered environment they need. And obviously, the amount of ammonia available is the raw material for nitrite production.
Makes perfect sense. And then alkalinity itself, we've seen it pop up as influential for others. What predicted its levels?
Alkalinity prediction was most influenced by transparency, total ammonia, and nitrite.
So it's being influenced by the things it also influences, a feedback loop.
Exactly. It shows alkalinity isn't just static. It gets consumed by processes like nitrification. It's affected by biological activity linked to light, linked to the nitrogen compounds. They're all locked together.
Okay, so for DO, ammonia, nitrite, and alkalinity, they found the key drivers and showed that predictive models, especially that combined one, could forecast them pretty reliably. But you mentioned pH earlier was maybe a bit different. How did the models do with pH?
Yes. pH was the tough one, the outlier. The models really struggled there compared to the others. The agreement between the predicted pH and the actual measured pH just wasn't nearly as strong.
Not entirely surprising, maybe. pH can be incredibly dynamic.
It can be. And the researchers suggested it likely came down to the specific inputs they were using for the models in this particular setup. pH is affected by a whole host of things, maybe more than were captured in the daily measurements.
Like what, for example?
Well, think about the carbon dioxide balance respiration versus photosynthesis minute by minute. Also, the exact amounts and types of any buffers or chemicals added. Even things like rainfall chemistry in an outdoor system. If those aren't fully quantified and fed into the model, predicting pH accurately becomes very challenging.
Right. Garbage in, garbage out, essentially. Or rather, incomplete data in, weak prediction out.
Pretty much. So predicting pH accurately definitely needs more work, perhaps broader data collection.
But still, the success with the other four parameters, DO, ammonia, nitrite, alkalinity, that's still incredibly powerful, right? What are the practical implications there?
Oh, the practical side is huge. Think about the standard way. Collect sample, go to lab, run tests. That takes time. Hours, maybe?
Yeah, easily.
The best model in this work, using data already available from the system, could spit out a forecast for ammonia or DO in about 15 minutes.
15 minutes. Okay, that's basically real time.
It's near real time, yeah.
Okay.
It shifts you from reactive monitoring, finding out hours later you had a problem, to proactive management.
You get a heads up before the ammonia spike gets critical or before the oxygen dips too low.
Exactly. You see it coming.
Yeah.
And then you can act immediately. Adjust aeration, tweak feeding, manage water exchange, maybe add buffers, whatever's needed. You're intervening based on a forecast, potentially stopping the problem before it fully develops.
That ability to anticipate must allow for much tighter control, keeping conditions in that optimal zone more consistently.
That's the goal.
Yeah.
More stable, optimal conditions mean less stress on the fish. That translates directly to better health, lower disease risk, higher survival.
And ultimately better growth and feed conversion, better economics.
Right. It's about using data, not just to see what happened, but to actively shape what's going to happen. It's a tool for boosting productivity and, frankly, sustainability, too.
It really does paint a picture of a shift in how aquaculture could be managed, integrating these data-driven tools, just identifying those key influential factors we talked about, like temp and nitrite for DO or transparency and alkalinity for ammonia. That alone gives you so much insight.
It tells you where to focus your attention.
And then using models that learn from your specific system's data, that offers a dynamic way to stay ahead.
And like you said, this was in an outdoor system. That's where you have all that extra variability from weather, sunlight. Being able to build models that account for that history gives you a level of foresight that's hard to match otherwise.
Okay, so let's try and wrap this up. The core insight here seems to be that these advanced analytical models, especially a combined approach, after you've identified the key drivers, they show real significant potential. They can accurately forecast several of those absolutely critical water quality indicators like dissolved oxygen, ammonia, nitrite, and alkalinity, at least in the context of outdoor red tilapia systems.
Yeah, that's the main finding. And the big practical takeaway is the speed. Getting those reliable predictions in, maybe 15 minutes versus hours, that allows for truly proactive, informed management decisions right there on the farm.
Now, pH prediction. That clearly remains a challenge. Needs more refinement, probably needs more detailed input data about carbon dynamics, chemical additions, things like that.
Agreed. That's an area for future work.
But the success with the other parameters is still really compelling for anyone running these kinds of systems.
Definitely. Understanding which factors are the heavy hitters for predicting specific parameters, and just knowing that these effective predictive tools are being developed, it should really empower you, the listener, to think about how data-driven strategies could be implemented, aiming for better efficiency, better fish performance, better sustainability.
It certainly changes the possibilities for managing water quality almost in real time, which leads to a final thought, maybe. Given that clear success for most parameters, but the difficulty with pH, it makes you wonder, what other factors, maybe things we don't commonly measure continuously today, other environmental or biological variables could be the key to unlocking really accurate predictions across the board, including pH?
That's a great question.
And thinking bigger picture, as continuous automated sensors become cheaper and more common, how might that sheer volume and frequency of data totally change the game? How might it transform our ability to predict and optimize water quality in all sorts of diverse aquaculture settings, well beyond this specific outdoor tilapia system?
If you enjoyed this episode, make sure to follow the Aquaculture Podcast Show on your favorite platform. And don't forget to follow us on LinkedIn, Instagram, and Facebook to stay updated on the latest episodes and industry insights. Thanks for tuning in, and we'll catch you next time.